Today we're going to talk about two topics. They're kind of related. One is heat engines, and the second one is the second law of thermodynamics. It's easy for us to produce heat from work. Rub your hands together. We do it all the time. You're doing work, but you're producing heat. Take a paper clip or another piece of metal and bend it back and forth, back and forth, back and forth. It gets hot right at the bend. You're doing work, it turns into heat. Pound something. Take a hammer and hit a piece of iron 20, 30 times. Both the hammer and the piece of iron will be warm. Stretch a rubber band. Grab a rubber band and stretch it out. Produces heat from work. That's easy. It's quite a bit harder to take heat and turn it into work, although it can be done. In fact, it's so hard that it's only been a couple of hundred years ago that the first practical heat engines were developed. Here's what a heat engine is defined as. It's a device that changes heat into work by undergoing a cycle of changes. That's a heat engine. So there's not just one change, but there's a change that can return back to its original starting point and then start over again. That's a heat engine. This is a little schematic device that we can use to model what's going on with energy flow in a heat engine. The heat engine takes energy from a heat source, like burning gasoline or something like that, and the heat engine transforms that into work that it now does on the surroundings. That's the idea behind a heat engine. Take heat, take Q, and change it into W. Well, let's think about a heat engine as a gas system. They don't always have to be gas systems, but the most common ones certainly are. And it goes through a cycle. Let's think about what would have to be the first step. Well, if we want to get the most work out of a gas, we want to have it undergo, as we saw in our last notes, we want to have it undergo a isothermal expansion. So we would move the gas from here to here isothermally. That would be ideal because that would give us the most possible work out of this system. Now this is a cycle, so we've got to get back to the starting point somehow. There are several options for this. One option is we could go straight up isochorically to a point 3 and then go back. But that's kind of dumb because if you take a look at the work here, this is the amount of work that we get out. If I shade the other direction, this is the amount of work that we have to do to get back to the beginning. Well, that's not a work-producing system. It takes more work to get back to the starting point. Here's another possible option. Just go straight back the way you came from. Go isothermally right back to starting point number 1 and have your cycle be back and forth on this isotherm. Well, that's better, but it's still not very good because it doesn't produce any net work. Here's the work done in the expansion. Here's the work you have to do to get it to contract. It's the same amount of work, so no net work is produced. So clearly our return path has to be down here in this area. You can't return either on the isotherm or up here and expect to get any work out. If you want to have this system return back to its starting point producing work, you have to drop to a lower isotherm. Well, what's the best way to drop to a lower isotherm? There's more than one way to go, so let's think about our possible options. One is we could drop straight down to point 3 through an isochoric pressure drop. Well, there's no work done, so that doesn't give us any extra work. So that's probably not the best choice. If we were to go like this way to a point 3 over here, there would be an expansion and then there would be some amount of work done here. Now, if we expand in a way that produces no waste heat, well, that would be the adiabatic expansion. The best way that you can get to a lower isotherm is through an adiabatic expansion. So that's going to be your next step. Now we have to find a way to get back to the starting point of the cycle. We've now done an isothermal expansion, then an adiabatic expansion. Somehow we got to get back to the original starting point. Here's one possibility. What if we just did an adiabatic compression and went straight back up to our starting point and had that be our cycle, 1 to 2 to 3 back to 1? Well, there's a disadvantage there because remember, the area enclosed by a cycle is the amount of work done. We could have a bigger area if we came back in 2 steps at a stopping point over here someplace, somewhere in between. One thing is definitely true then. We're going to have to lose heat. Because we're not going straight back here with no heat loss, that would be adiabatic, we're going to have to be down somewhere in this zone with our step 4. And that means we're going to lose some heat. So that means the model of a heat engine really isn't true unless it includes a heat loss. So this is really the model of a heat engine. There's a heat source that produces some heat. We'll call that QH for hot. And then work is done to the surroundings. But there also has to be loss of heat. There is no engine that can possibly operate without losing some heat. So there's a heat sink, T low, that we give Q low. So you start out with a hot source, you dump some heat to a heat sink, which is at low temp, and then some of the energy that went in comes out as work. So no heat engine is perfect. Here are two pathways that could go back to the starting point. One involves an isobaric change, where you just cool the fluid down isobarically, keep the temperature the same, and then go up. And the other option would be isothermal, where you follow an isotherm and then heat it up, increase the pressure back to the original temperature. Well, obviously, the one that gives you the biggest area would be the isobaric change. However, in an isobaric change, you have to have some energy come out. There's a Q that has to be lost to the surroundings. If your objective is to lose as little energy as possible, you don't want to choose this. You want to go back isothermally so that the work done and the Q lost are the same. So we're not going to choose an isobaric path. We want to take an isothermal path. It saves the most energy, wastes the least heat. So now we have a point 4 that's on this line, on the low isotherm. How do we go from there back? We have two choices. Isothermally compress back to the original volume and then have an isochoric change back to the original temperature. Or we could do an isothermal change part of the way back to the original volume and then do an adiabatic change from there. Here we'd have more work done. However, to make this gas go from this temperature to this temperature by increasing the pressure without increasing the volume, we're going to have to put energy in from the outside, from the heat source, and that's going to waste more energy. Here, with an adiabatic change, Q is 0. There's no energy flow through work, just a little bit of energy flow in this thin sliver of work that has to be done. Adiabatic is a better choice than isobaric, and so this is going to be your ideal system. This is the best way that you could possibly have an engine work. This ideal engine is called the Carnot engine and operates on this cycle called the Carnot cycle. It's named after Sadi Carnot, a French physicist and engineer who figured this out. And so the Carnot cycle involves this. There's a isothermal expansion, adiabatic expansion, another isothermal compression, and then another adiabatic change, a compression back to the starting point. So that's the cycle. Now, recalling that the shaded area is the work done, that's the work that your engine can do. The Carnot engine doesn't really exist. The Carnot engine is a theoretical engine. No real engine is as efficient as the Carnot engine. However, the Carnot engine is useful because it gives us a maximum theoretical efficiency that any real heat engine could be compared against, so that we can figure out how bad or how good our engine really is. So there's some value to it. Thinking about efficiency, our efficiency is equal to the work output over the energy input. Well, the energy comes in from the heat source, and so this is really QH, the energy that has to come in from the hot energy source. So if we could figure this out, for the Carnot engine, we would have the maximum efficiency. Let's think about this in terms of the heat flows that are present in our theoretical engine. Remember, from the heat source we have Q hot, and to the heat sink we have Q low. Let's see if we can find out some relationship that will give us efficiency in terms of the hot and low energy flows through heat. Let's track this by looking at all the energy changes that happen during the Carnot cycle. First of all, we have an isothermal expansion. What happens in an isothermal expansion? Well, we use these little schematic diagrams in the last notes to kind of track this. In this expansion, there has to be work done. So the process, the engine itself, loses energy through work. We're going to call this work 1, 2, because it goes from step 1 to step 2. The energy at step 1 and the energy at step 2, however, are the same. And that's because in an isothermal expansion, you stay on the same temperature curve. So there has to be a Q that goes in. Q1, 2, we could call it, or Q hot, because this is the energy that comes in from the hot source. So Q hot equals work 1, 2, and that means energy at state 1 and energy at state 2 are the same. So E here and E here, those are equal to one another. Looking at the next step was an adiabatic expansion. Adiabatic expansions, by definition, have no energy flow through heat. However, this is an expansion, so there is a loss by the system in work. We're going to call this work 2, 3, because it's the work from step 2 to step 3. So that means the energy, the change in energy, is equal to the work done, work 2, 3. So E3, well, that's just equal to E2 minus the loss due to work. But E2 was really E1, so E1 minus work 2, 3 is another way of saying how much energy is at E3. So here it's E1 minus the work done in step 2, 3. That's the energy at step 3. Well, the next step is an isothermal compression. In an isothermal compression, work is done on the gas, so that means we have a work input to the system, but Q has to be lost in an equal amount, and this is Q low. This is the loss to the low temperature heat sink. So this is work 3, 4, because it's work from step 3 to step 4. So we could say work 3, 4 is equal to Q low, the low temperature heat loss, and because of that, E3 equals E4. There's no change in internal energy in this process. The work is matched by heat loss. But remember that E4, because it's equal to E3, is really equal to E1 minus the work from step 2 to 3, because that's what E3 was. The last step is an adiabatic compression. Now in this adiabatic compression, we're going from here to here, 4 to 1, and that takes work. We'll call it work 4, 1. So there's an input to the system, but there is no Q in an adiabatic change. So that means the change in internal energy here for the system is equal to the work. It's work 4, 1. So that means E1 is equal to E4 plus the work done, work 4, 1. But E4 was, if you recall, E1 minus work 2 to 3. So substituting this in for E4, here's what we get. E1 is E1 minus work 2, 3 plus work 4, 1. Well, if you subtract E1 from both sides, here's what you get. 0 is negative work 2, 3 plus work 4, 1. So here's what this means ultimately. Work 2, 3 is the same as work 4, 1. So looking at this cycle now with all of our energy exchanges on there, work 2, 3 and work 4, 1 are the same. So we can sort of net them out of our equation. So here's what this means ultimately. The net work done by this system doesn't include those adiabatic expansions and compressions. The net work done on the system is just the work that went out through 1, 2 minus the work that went in from stage 3 to stage 4. However, those were both isothermal, and so work 1, 2 and QH are the same. So we can rewrite this. And work 3, 4 and QL are the same. So that means our net work is QH minus QL. So what's our efficiency? The maximum theoretical efficiency based on the Carnot cycle is this. Work out, which is QH minus QL, over energy in. This simplifies to 1 minus QL over QH. So if we know the energy flow from the high temperature source and to the low temperature sink, 1 minus that ratio gives us the maximum theoretical efficiency. That could be pretty useful. It also turns out that the ratio of temperature to temperature low to temperature high is the same as the ratio of energy low to energy high. This requires calculus to prove this. I can do that if anybody knows calculus and is interested, see me. But otherwise, just have to trust me. And so we have another expression that's even more useful in many cases. Maximum theoretical efficiency for a heat engine is equal to 1 minus low temperature, high temperature. So if you know the operating temperatures of the heat sink and the heat source, you could figure out the maximum possible efficiency for any engine operating between those two temperatures. Here's an example problem. What's the maximum theoretical efficiency of a heat engine that operates between a heat source at 700 kelvins and a heat sink of 273 kelvins? Well, the maximum efficiency is given by 1 minus T low over T hot. So that's 1 minus 273 kelvins over 700 kelvins. And that's equal to 0.61, or about 61% efficiency. Here's another example problem. An engine takes in 550 kilojoules of heat and exhausts 270 kilojoules in each cycle. The first question is, what's the maximum work this engine can produce per cycle? Looking at our schematic, we have energy coming in from the high temperature source, and it says that that's 550 kilojoules. Here's our engine, and we're releasing energy to the heat sink, T low, and that amount of energy is 270 kilojoules. So here's Q hot, here's Q low. And the only other thing that's happening energy-wise is we've got work going to the surroundings. How much work? Well, energy has to be conserved here, so the difference between 550 kilojoules and 270 kilojoules has got to be work. Work is Q hot minus Q low. So work is 550 kilojoules minus 270 kilojoules, and that leaves us with 280 kilojoules. Next question is, if this engine completes 500 cycles per minute, what is its maximum power output in kilowatts? Well, going back to our problem here, we know that what power is. Power is equal to work done in the time that it's done. It's a time rate of doing work. Well, we know that this is doing 280 kilojoules in every cycle, but we also know that this is doing 500 cycles per minute. So if it's doing 500 cycles a minute, we get a power, kilojoules per minute. But we want kilowatts, which is kilojoules per second, and so we'll do another conversion, and we know that a minute is 60 seconds. This comes out to 2333 kilojoules per second, or kilowatts.